Okay, so in today's class we'll quickly go through analog layout. So we have looked at it on and off over several classes. So today we'll try to do a comprehensive review of this. So first of all, has everyone heard of the word layout? As apart from design, I guess some of you guys have. How about the others? Have you heard of the term layout? IC layout? Have you done a digital ICs course before? No, some of you have not. Okay, so basically the idea is, let us say, okay, so as you did with your projects, you have designed your circuit. The next step is to get it ready for fabrication, and layout is an important part of it. So it is basically a geometric representation of your circuit, which is going to be laid out on, which is going to be fabricated on your IC. Okay, so that's all you're doing. It is a top view. We have seen before top views of circuits. So you're going to take your circuit, which is in terms of transistors, nodes and so on, trying to lay it out in terms of the drain, source, gates, bulk connections, right, on the IC. So we'll go back to the top view we've always seen. So what you'll have to do is, you'll have to give a connection for the gate. So let us say this is the drain and this is the source. So you'll have to give a connection for the, so what happens is the connection of the IC to the external world is through metal lines. So you get the IC fabricated. So that includes the diffusions, the gate polys, metal lines which connect to both of these, interconnections between different transistors in the circuit. Eventually you will go out to pads, which are the external periphery, usually the external periphery of the overall IC, that gets connected to the external world using a bond wire and through the leads of the package. Okay, so you also need to make sure you have the option of adding external metal connections to the gate, drain and source. So the way you would normally do that is, you would have you have what are called vias or contacts. So which vias are usually between different metal lines. Contacts go from the substrate or poly to metal lines. The interconnections between two metal lines. And then what you would do is something like this. Let us say this is a metal line. This could be another metal line. And this could be a third metal line. These should be the gate, drain and source connections. It would look something like this. Okay? So this is a metal line. Oh, sorry. So this is a metal line, okay, which is going to connect. So you could have, let us say, the drain of this transistor goes to the source. Let us say goes to the could have something like this. Let us say it went to the gate of another transistor. It would look like this. So you have a metal line connecting from the drain of one to the gate of the next. Right? This is one example. This shaded region in here is actually the contact. It connects the diffusion to the metal line. Is that okay? So you have to make a connection between your diffusion, silicon diffusion, and your metal line, which is how so basically this via this contact, you have your diffusion like this, you have a metal line like this. It's basically a vertical contact between those two. Okay, and so this is remember that the vertical dimension is the width of the transistor. Correct? This is the length of the transistor. So the drain current in this case will flow out from the, let us say it's flowing out. It would flow out from the diffusion vertically through these contacts and then horizontally through these metal lines. Okay? So the vias are usually, they are very similar, okay? Contacts are usually from diffusion or poly to metal lines. Okay? So if you look at if you just look at the, so let us say it look like this, drain, source, this gate, right? Then what you would have is, this is the side view. Of course, metal lines could look something like this. This will be the thickness of the metal line in the vertical dimension, right? You don't know where it's going on the horizontal side, but I've just shown it like this. Could be something like this, okay? And now the metal too can have different levels. So you have different metal layers. So you have all the way from, so the lowest metal layer is usually called metal 1, and then metal 2 and metal 3 and so on. You can have all the way up to some, 5 or 6 metal layers, maybe even larger number. Okay? Oh, sorry. What will the contact? So if you have current flowing out, right? So you have drain current. Let's say source to drain. Flow out like that. What is that contact? Oh, I see. The contact material. Contact material is usually some kind of metal, or it could be a metal alloy. Okay. It is so it is usually okay. So because it's small and thin, the resistance of the via could be quite large. Okay, but at the end of the day, it's a conductor which you are just using to. It needs to be a material which bonds well with, of course, the upper metal layer as well as the lower silicon substrate. Same with via also, except in the case of vias, so you could have a. Let me draw it in green. You could have something like this. This would be M2 and this would be M1. Correct? Is that clear? So I have just shown a second metal layer with a via in between. This is a contact. Okay? Okay? So now there is one more detail which we have not included in this. What is that for the transistor? How many terminals does the transistor have? Bulk. We have not included the bulk connection. So what is the bulk connection here? It's connected to the lowest potential. But first of all, what is the bulk layer here? We have shown the 3 layers. We have shown the drain and source conduction layers. It's a substrate. The background is actually the substrate. So all of this area is actually just the substrate. However, the substrate resistivity could be high, right? So you need to make sure you give a good, and plus the connection of the substrate to the lowest potential could happen globally for the overall chip. So you need to give it local contacts. So normally what you would do is, you would quite possibly put in substrate contacts for the separately for this transistor alone, and then you would probably connect it on metal. So in this case, let's say it's connected to ground. Okay? Because you are not going to rely on the very resistive connection, right? The global connection of the substrate could be happening elsewhere. So what you are going to do is to make sure these transistors have a good ground connection. You are going to put in contacts connected using metal layers to ground. Okay? Is that clear to everyone? Okay. Okay. Now let us say you had the option. So this is in terms of the width of the transistor, and so what all dimensions can you see? I showed the width and the length. So you have this third dimension. I'll call E for now. I'll call this E. But what should the size of E be? So we have 3 dimensions here. This is the length of the transistor. This is the width of the transistor. And there seems to be one more dimension here. I can actually make the transistor this wide also. I mean the lateral dimension this slightly wider. That is not the width of the transistor, that's for sure, because width is the vertical, because we are looking at the top view of the layout. So what is that parameter E? And how do you decide it? Huh? 2 times the L minimum. Why? It should be larger than the metal line. Okay. So that is, it should be, you're saying it should be larger than this guy. Okay. What else? Anybody else? First of all, is E a design parameter? As far as design goes? Huh? Depends on the technology. No, definitely E depends on the technology, just like L and L-min and W-min depend on the technology. That is true. What I am asking is, if I change E, will it affect your design? Or should you change E? Is there a recommendation on what E should be? Parasitic? What parasitic? Capacitance. Drain bulk capacitance. So of course, if you make E wider, you would increase your drain bulk capacitance. Right? What is your drain bulk capacitance? In this case, let us call this the drain bulk capacitance. We are going to look at it in a little bit more detail. So, if you make this dimension wider, you are going to get more drain bulk capacitance, and that we know is something to be avoided. So you would probably want to have E to be as small as possible in many cases. Can you think of a reason why you would want to make E wider? Yeah, we are going to look at that. I think we have looked at it in a little bit of this thing, but we'll look at it again. Okay, so we are going to share the drain of one transistor with another. Why do you have to make it wider? You can connect it together, but doesn't mean you have to make it wider. You can share it without making it wider. Reduce the contact resistance. So how would you reduce the contact resistance? So, okay, in this case, what is the contact resistance? So if I give you resistance of a single via is 2 ohms, or let's say 6 ohms, right? What is the resistance of the contact resistance here? So if it is 5 ohms, it's 2.5 ohms. Let's say in this case it's half, right? So what you are telling me is, you are giving me a reason for increasing W. Can you, what do you do if you increase E? You can put in 2 rows of contacts. You can. So decreasing contact resistance is one reason. Okay. Anything else? Current density. Okay. If you have this is related to the output stages we were just discussing. If you are designing a power stage which is drawing a lot of current, each of these vias will have a limit on the amount of current they can carry, otherwise they will melt. Okay. You might need to have a minimum number of vias based on the current carrying capability. Because of that, you might be forced to increase E even if you don't want to. Okay. These are your multi-finger transistors. Okay. So let us say I take the same transistor but split it into 2 fingers, each of half the width. This would look like this. You would want to make something like this. So this is these are the 2 transistors you have. Okay. all I've done is I've taken the same transistor, split it into two fingers. Which is better and why? The right side one is better. Why is that? Drain capacitance. Why? Why is the drain capacitance lower? W is W by 2. Right? So it definitely looks like the drain capacitance is lower. Is that right? This is a case where you are sharing the drain, right, between two transistors. Okay, it doesn't have to necessarily be wider. In fact, you would probably make it minimum just enough to carry the current. That's good enough because you are worried about the capacitance. Okay. What about the source capacitance? So if you look at these cases, so I'm going to call this small d. This is W. This is E. What is the total drain bulk capacitance? First of all, what all components can you see for the drain bulk capacitance? You have some drain bulk capacitance like this. Definitely. Right? On the bottom side. What does that depend on? It depends on the area of the bottom. What is that? E into W. Correct? So I'll call that the bottom. What else? You also have the side walls. Right? You also have capacitance like this. Correct? What does that capacitance depend on? It depends on the perimeter, because the distance d is actually fixed for a particular process. That you cannot change. Okay? So it just depends on the perimeter. Okay? To E. Okay? The reason is so if you take a particular process, you have these two parameters Cj and Cjsw, the junction capacitance, and they will be given as parameters. In this case, Cj would be capacitance per unit area because E and W are under your control. You can make them wider. Whereas Cjsw capacitance per length, so it will be like capacitance per micron, whereas the other one will be capacitance per micron squared. Okay? You can calculate the capacitance in the two cases. So you can, in terms of Cj and Cjsw, you can calculate the two cases, just multiply by the perimeter and the area, and you will find that of course the drain bulk capacitance visually is reduced, source bulk will be slightly increased. So it seems like it's a good trade-off. In many cases, if you use common source amplifiers, differential paths, you're not worried too much about the capacitance of the common source node. You're more worried about the drain capacitance. Right? So if that is the case, you are more interested in reducing that. Therefore, you would try to go in for this. What is the other advantage of doing this? You have some distributed resistance along the poly. The poly is not as good a conductor as your metal. So you have some distributed resistance, which is usually which is called the gate resistance. Okay? If you try to make the width of the transistor very long, let us say you had to make a transistor 200 microns by I don't know 1 micron. If you make a 200 micron, if you make it as a single transistor with W being equal to 200, you are basically routing, because what happens is the gate connection you make is somewhere up here, right? The transistor stretches all the way, so you have a problem, right? Because instead of being directly connecting to the real gate, the real gate is actually a distributed gate along this, right? You can think of the transistor as being split up as multiple slivers, all of them in parallel, right? The last guy has a very, very large gate resistance. How would you solve it? Huh? You can't give a gate contact on top of this, on top of the transistor. That's why specifically I have shown the gate contact being made outside the transistor. You cannot make a gate contact on top of the transistor. What? Okay. Definitely gate resistance will be lesser, right? So fingering is one more advantage of reducing the gate resistance. Correct? Okay. What else can you do? Can you do anything else? Okay, so you increase the number of fingers. You can make it 4 fingers, 8 fingers. So what is the limit? Why won't you just have, you know, a very, very thin transistor, very long? Right? It seems, why not make it W by 4 and... Yeah. Can you repeat that? Correct. Correct. There doesn't have to be current flowing through this. Is there a difference between this and this? Is there a difference between these two cases? There is no current flowing through it, right? What is the difference actually? Huh? Why? If you consider the gate capacitance, so it becomes definitely more significant at higher frequencies, right? Because you are worried about the gate source capacitance. Okay. Anything else? What else? What are the other effects of having a resistor? This is actually a physical resistor, right? Yes. Noise, right? So this, you can have gate resistance noise from the transistor. So if you had a 200 micron long transistor, you will definitely see noise from the gate resistance. So splitting it into multiple fingers is very good. What else? I can also do this. Nothing prevents me from adding one more set of contacts at the bottom also, as long as it's outside the transistor. All I would do is I would do something like this, maybe. I may do something like this to connect to the gate. It's perfectly, legal and perfectly fine. It will probably help you. In many cases, you probably want to do that, right? Doing dual gate contacts is usually considered a good practice, unless you run out of metal layers and it's not needed. In some cases it may be needed, some cases it may not be needed. You will have to make the decision. In most cases, it is very useful. Okay. What else? Yes. What is? That is the total sidewall capacitance. So you have the vertical capacitance and you have the sidewall capacitance this way, all along the perimeter of the device, right? So it's like a tub. Think of the bottom of the tub, think of the sidewalls of the tub. Everything surrounding it is a substrate. So you have to include the total capacitance to the substrate. You'll have a vertical component and you'll have a horizontal component. Horizontal component is a sidewall. It depends on the area, but the depth is fixed. So it depends only on the perimeter, right? Okay. Now what about other layout practices? So let us say, okay, so now we are done with the basics, right? So you take a transistor, and you split it up into multiple sections and so on. Okay. Now suppose you want to have good matching between, let's say, resistors, capacitors. We have discussed some of these things. Suppose you have two resistors. What are the practices you would use to make sure they are well matched? Yeah, so let us say you want to build an amplifier of gain 2. So you have a resistor and a feedback resistor. Right? So gain depends on R2 over R1. You want to make sure that tracks well with process. How would you take care of it? So let us say you had something like this. You wanted to lay out R1 and R2. What would you do? How do you lay out R1? Can you lay out R1 vertical and R2 horizontal? Why not? There can be some gradients in the process, the way that things are fabricated. Because normally these things are stuck in a furnace, there may be a temperature gradient. Usually the diffusion happens from, it may not be uniform, may come from a particular direction. There are lots of things. Over a chip, you can have a gradient in any direction. You don't know, right? Somebody might turn the wafer and put it in for one particular layer. You don't know, right? So you want to take care of these things. So we have discussed this before. So let's say if one resistor is this, other resistor is this. You don't want to do this. You want to lay it out as maybe as two sections. You may do it this way. Okay. This will make sure. So these are your two resistors. Okay, you make sure they are the same orientation. What else? Place let us say this was R1, R2. So one thing you can do is, so you can make this R2, R1, R2. Can you do this? To make sure that there is a gradient from one side. This will be slightly better. Quite possibly it will be better than the previous case. You can't say it will be perfect. It will be better than the previous case. So if there was a gradient, let's say in this direction, right? One other thing, like he mentioned, you can actually add dummies. Okay, that will make sure if there is any gradient effect, if there is any. So what happens is you have to be careful about the environment of any device you lay out. Yes. No, you can place them apart, right? You can place them wide enough apart such that you don't have a lot of capacitance, but close enough such that the gradients are good, right? So the idea is you are trying to make the environment around. So R1 has two resistors on either side. You want to make R2 also the same way. Correct? Okay. What else can you do? How wide would you make R1 and R2? Would you make them very wide, very thin? What are the trade-offs? Okay, depends on the current they have to carry. So let's assume that is not a problem. Let's say they are carrying very little current in this case. Wider, why? Right? The wider you make the resistors, you would reduce random mismatches. Remember that the random mismatches depend on the overall width and length of the area of the device. So the wider you make it, you will make the resistors match better. Okay. So why not make them extremely wide, 10 microns, 20 microns wide? You have to worry about the capacitance now. Okay? And of course the area occupied, because if you talk about 100 ohms, 1 kilo ohm, not a problem. If you're talking about 100 kilo ohms, becomes a big problem. And same thing for the capacitors, not a lot of difference. Now how about if you have, let us say, if you have these transistors like this is a differential pair. Okay, you want to have very good matching between these two. How would you lay it out? How would you lay this out if you want to have very good matching? So of course, the brute force way is to do this. So let us say you do multiple fingers. You can interleave the two devices. Why is that? The reason you can interleave them is because they share a common source. Just like in reality, these are actually interleaved transistors. Remember, look, if you look at this layout, if you look at the way, if you look at this thing, these are actually two transistors which are interleaved, right? Which are sharing a single drain. You can do the same thing. In this case, you can make them share a single source and you can interleave them. So instead of doing this, you can do this, source, drain, source, drain, source, drain. Let's say something like this. So D1, D2, D1. So let me make it something like this. Right? I have D1, D2, D1, D2. So let's say in this case, you can interleave them this way. Can you do it? So this will take care of what? Gradients in which direction? This will take care of horizontal gradients. Will it take care of vertical gradients? To some extent it will. But if you want to do an even better job, will it take care of some random gradient from any direction? Can you do better? So one way to do better is to do this. Right? You can split it up into two sets of devices. Actually, so this is called a common centroid layout. Right? This will take care of gradients hopefully from any direction. Vertical gradients are the same for both. Are horizontal gradients the same for both? It's better than the previous case, but is it the same for both? Not necessarily. That's right. It will take care of vertical gradients also, but in this case, vertical, if it's perfectly vertical, there's no problem. Right? Perfectly vertical, there's no problem even in this case, because everything is, uniformly affected. Right? Okay. So what is the problem with this kind of layout? What do you think the problem could be? Or is there a problem at all? Huh? No, that's okay, because they can be, so I can do something like this. It should be even better. Right? So this is called a common centroid layout. So this way, if you split it up as M1, M1, M2, M2, vertical gradients no problem, horizontal gradients no problem. This is even better than the previous case for horizontal gradients. Right? Okay. What is the problem with this? Now remember that you now have to make these connections. Forget the, I've just shown the gate, but you have to connect the gates, drains, sources across, right? You can never get those to match, because you cannot have two metal lines on the same layer crossing over, so they'll just short, right? So you will necessarily have to use either different metal layers, so you may need to use M1 and M2 maybe, something like that, in which case the capacitance is slightly different, and quite possibly the resistance of the metal layers could be slightly different. Okay? So in this case, capacitance wise, it will not match, but basic, DC mismatches, that is low frequency mismatches, would be much better. Okay. Of course, you are never going to lay out a transistor like two transistors, matching transistors like this, one horizontal and one vertical, right? But suppose I gave you two choices. Which would be better? The left side one? Why? No. These are two independent transistors, but you want them to be matched. Okay. Well, let's say they don't share a common source, but you still want them to be matched. Let us say it's a replica. Remember that op amp we had this replica in the common mode feedback loop. Let us say these are two replicas. Because one is a replica of the other. Quite often you would prefer to do the second case. The reason is you can have what is called a shadowing. You can read up on this in Razavi's book. You can have what is called shadowing. So when you have a source drain, the implant doesn't come in, it comes in at an angle. Okay? So what will happen is one side will get shadowed, and that will affect the transistor next to it. Okay? In one case, so what happens is, if you look at the process, so you take the gate and then you put in the source drain implants. First you build the gates and then you put in the source drain implants, and they come in at an angle. Okay? So if they come in at an angle at I think it's 7 degrees from the vertical. If they come in at a small angle, you will get shadowing on one side. Let us say if they come in from 7 degrees on this side, they come in at 7 degrees, something like this, you will get shadowing on this side. Which do you think is going to be better? First one. Second one. Why? Area wise. Okay, suppose area is not a big concern, not a big problem. By the way, area is not a problem between the two cases. It's not a big problem. Sharp corners would be a problem. In what way? Yes, sharp corners would be a problem. So you would have, if you have a large current flowing through this, you would have current crowding here along the corners, right? What will typically happen is, it won't make a big difference, at least for analog circuits, over the short term, but over the long term, you would have the metal getting redeposited. Okay, that's called electromigration. You prefer not to make very sharp corners. This would typically be much better, the one on the right side. Okay, than the one on the left side. Okay. Suppose you have two differential lines, you probably want to maintain routing something like this, some kind of differential routing schemes. You want to make sure the routings are also well matched between the differential sides. Okay. Time scales, a few years. Right? Over the lifetime of the device, things will change. That's all. I'm not talking about a few minutes or a few hours. Right? Over several, if the device is continuously used, over several years you'll see it. So this has more to do with reliability.